Well, good day, everyone. Welcome back to Frontlines and Faultlines with Mike Kelly. And really good to have you back today because it's a very important session that we're going to have with our guest, Will Howard. And really, this is part of the series that we're going to do to look into disaster issues that are facing Australia and also what the implications that poses for not only policymakers and people who have to really work our way out of the worst effects of climate change if we accept the science of it, and we'll talk about that. But also, we'll finish up by talking about in future episodes what the experience on the ground has been to some of the more catastrophic, large-scale disasters that we've faced as a nation, and sort of challenged me personally as the former member for Eden Monero, and also what we do about that, in terms of practical and first responder regimes. So to introduce our guest, we've got Dr. Will Howard here with us today. And Will is an incredibly authoritative person to be talking about this. And you often hear people joking about, well, I'm not a climate scientist, but Will Howard is, and really well credentialed. I mean, he's got a PhD from Brown University, which was in the relevant science areas that are relevant to understanding this world. But his current role is as the lead scientist at the Australian Government Climate Change Authority. So he's the lead scientist, but the depth of background behind that is quite extraordinary. So he was also the lead climate scientist with the Department of Agriculture, Water and the Environment. He was the climate science advisor also in the two departments of environment and water and agriculture as they were at the time. He's also had a lot of deep experience in practical applications and research in relation to climate science. So, he's been out there in the Arctic areas, as you can see from the background there. And what we're going to do today is try and navigate through those challenging waters and hopefully won't go down like the Titanic. But it's really been a tremendous lifetime's work effectively with Will. And there's nobody, I don't think, in Australia more authoritative or more able to speak to us about this issue. So really delighted to have you on board, Will. And if there's anything else about your background that you think's relevant to all of this, let me know.
Just only one slight correction. I actually finished up earlier this year at the Climate Change Authority. It was a great honor for me to be the lead scientist for 3 years. But I also I finished up. So
Are you retired now, mate?
I'm now technically retired.
Okay, so you can speak freely, even better.
I can.
Awesome. No, that's great. But just an incredible lifetime's experience. What drove you to get involved in this area in the first place?
Well, I was always fascinated by the ocean and the earth. And I've loved it always since a child. I spent time near the sea or on the sea or in the sea. And so I always loved nature. I think, my mother used to take me to places like the Museum of Natural History in New York um, and take us on nature walks and things. So I got very interested in, just natural world and how it worked. And at uni and later in my graduate PhD research, we got very much fascinated by some of the research that was being done on how climate of the Earth had changed over time. This is over the so-called ice age cycles, over hundreds of thousands of years. And I just thought that was the most fascinating thing I'd ever heard about. I heard a lecture on it, and I thought, wow, you can actually geologically, reconstruct and effectively make kind of a time machine to understand how the Earth's climate has evolved. And I ended up doing my PhD in that space. And that very much took me into the space of understanding what's happening to the Earth's climate now, and where it's likely to go in the future. So, those two things, intellectually are actually very much intertwined for for people who work in that field. And so for many of us, early on when I was a student, certainly we understood the idea of climate change, the idea that humans were influencing the climate in a number of different ways, including adding greenhouse gases. At the time, it wasn't really, it was just an interesting scientific question. It didn't have the political sort of angle or aspect that it has at the moment. Uh, but certainly we could see the policy implications
Well, that
and
background.
where it would take us in the future. And so certainly now, of course, we're very much aware of the challenge that it presents.
Right. Well, that background must have been really fascinating from the point of view that the science behind it. It's like reading the book, The Story of the Planet, in many ways, but it must also give you another complete perspective on time when we talk about the eons involved in those processes, geological and others. So,
That's right, and climate change is a long term
mhm,
environmental challenge.
right.
So it differs from other pollution problems that we've faced in the past, where in many cases, we're talking about local air pollution or
Mhm,
local, say, water or river pollution. We've been very successful, and those are environmental success stories of
mhm.
remediating those forms of pollution. Uh, the climate change problem is a bit longer
Right.
time scale, so it'll take a
Yeah.
bit
I would
longer
agree.
to bend that curve.
Yeah, I suppose the comparison there is for a long time we talked about the ozone layer and the effects of certain types of emissions on the ozone layer and the remedial legislative and other actions that were taken to prevent the sorts of emissions that were having that effect, and then the short term benefit to the ozone and remediation and bouncing back of the system effectively. So that was like an incredibly short period of time when we talk about the sorts of background work that you've done on the planet over those massively long, extensive periods of millions of years.
Sure.
So, but Will, how would you, if you wanted to sum it up simply, what's the theory of climate change? The issue that's the burning one for present day people.
The Earth's climate, all our energy, virtually, in terms of the energy that drives our weather systems and makes our planet habitable, is coming from the sun. And the Earth balances its own temperature. In fact, the Earth is habitable because it does have a layer of atmosphere that includes greenhouse gases. Okay, without those greenhouse gases, we would not be a habitable planet. We'd have a free surface. So what those do is they interact with the outgoing radiation. So radiation comes in as sunlight, which you can see, and it's coming into your window and mine as we speak, and that interacts with the surfaces on the Earth, land, land and water. The Earth heats up to a certain temperature, and at that temperature gives off heat in the form of infrared. It's not something you can see, and you feel it if you stand across the room from your glowing fireplace. Uh, on a cold day, you kind of feel that radiant heater. If you have one of those radiant heaters that sometimes people have in their houses, that's infrared heat. Now, the Earth has the balance, comes into balance with the energy that comes from the sun, and then it reaches an equilibrium. Now, before human, before this human influence of burning fossil fuels and adding greenhouse gases, mostly carbon dioxide, but also methane and a few other gases. Um, the Earth was was close to an equilibrium stage. It's always dynamic and it is changing. It was not just static, um, but it was at a certain temperature, um, and that was relatively steady for quite a few for millennia, not perfectly steady. Again, there's always variability, but now we've added greenhouse gases to the atmosphere. And just to put it in perspective, if we looked at how nature changed those greenhouse gases from the last glacial maximum about 20,000 years ago into the pre-industrial uh, era. We've now more than added that much greenhouse gases to the atmosphere. So in a sense, I tell people we have become a geological
Right.
force on the planet by adding those greenhouse gases that were previously, of course, stored in geological reservoirs as oil, gas, and coal, and added them to the atmosphere. Now the Earth, that's interrupting and capturing some of that outgoing energy. So to rebalance, the Earth needs to warm up to rebalance the radiative budget, the energy budget. And that's what's happening. That's what we see. Over the last few decades, the Earth has indeed been warming up, and it
So
will
this,
keep
this is
warming as we keep adding those greenhouse gases.
so this is the big issue on the debate, really, isn't it? We know that there's been changes to the climate throughout the eons of history of the planet, but the big issue now is what they call the anthropogenic aspect of it. Just how much impact are humans having here, or is it just part of the kind of natural oscillations of the climate? So, what would you say about those anthropogenic contributions? Is that, and you've said it's sort of on the scale of some of these natural events. So how much is that impact having an effect on the climate itself in the immediate term at the moment?
Well, we've warmed, the Earth has warmed from the baseline that we define as pre-industrial. It's warmed just a little bit under 1.5 degrees C. And just again, to put that into perspective, the whole Earth warmed somewhere between 4 and 5 degrees, again, coming out of the last ice age. So again, we're starting to warm the Earth at a significant fraction of that. That doesn't mean that, and there are natural forms of variability, things like El Nino and other things that also act on the climate system. But certainly we've turned this particular human influence into a large, and at least over the last few decades, probably the predominant uh, mode of altering the climate system. All the other things that can influence the climate system, El Nino, or the Enso, as we call it, volcanoes. There are other influences on the climate system, but we've certainly created a new influence or another influence that is larger and probably longer lasting than those other ones.
So with, the key element, you mentioned there are different types of emissions that relate to this, and methane's probably the most impactful, and you've got, I think it's nitrous oxide, and of course carbon dioxide is the one we focus on a lot, talk about mostly. And then you look at a planet like Mars, which, its atmosphere is what, about, 99% or something carbon dioxide. And so is that, I mean, is there a tipping balance here where you're going to end up with a surface like Mars, rather than the plant food that carbon dioxide is and the need you have to have for, a healthy environment?
It look that's a really interesting question. That point about are there tipping points, and that's certainly an area of active research. It's not always easy to know where we are relative to those kind of tipping points, in part because the system itself has such long timescales. You could be, you could already be through a tipping point, but we might not know it for some time. So ice sheets are an example of where you might put, could you have, and there are plausible models to suggest that some ice sheets might already be sort of past the point where they're committed to melting, but it still will take a long time. Uh, Others, it's not so, it's not straightforward to know. We know there are tipping elements that potentially could tip over into other states at certain levels of warming, but it's not easy to know exactly where you are relative to those tipping points, or if the system would tip at all. Certainly, it's been a very active area of research. It's a very challenging one. It's not easy. It's not easy to say um, from a policy perspective how close we might be,
Hmm.
if we're close to
Right,
those kind of tipping points. But it certainly adds an element of concern
right.
to
That
the way
wouldn't
we're
be.
pushing things.
But what would your view be? Like, there are people out there, you've probably heard these people say, like, it is just plant food, the more the better. Is there a point where, that equation changes, that, you're not going to have healthy plants out there with
Uh,
a
I
certain
think
level of carbon dioxide?
it is true, and yeah, it's true, and sometimes so it is true. Carbon dioxide is plant food. That's not that is not a scientifically controversial statement. People have done experiments, and sometimes people use carbon dioxide to make in greenhouses, hothouses, to make plants grow faster. So that part is out, and we can see some of the feedbacks. There are certain areas where you can see by satellite imagery uh, that certain areas that are sort of on the edge of deserts, we have seen some greening. So it's true that that's a feedback that tends to work against because those plants take up CO2. So not every feedback is a reinforcing feedback. That tends to, like sort of vicious circle when we see a reinforcing feedback. I mean, it's something that reinforces or amplifies the original push. Some things push back. So plant growth does push back, but plants are also limited by other factors like availability of water, nutrients like nitrogen and phosphorus. So, although it is true that CO2 is quote unquote plant food, um, it's only one of many factors that influence plant growth. So, again, it is true that CO2 does, all else being equal,
Hmm.
tend
Right,
to amplify or enhance plant growth in certain environments.
right.
But again, not enough to overwhelm or to balance the added greenhouse gases. And we know, for example, that terrestrial ecosystems take up somewhere around a quarter of all the carbon dioxide emissions that humans create. So we kind of know that. We know that the ocean takes up another about quarter, and about half remains in the atmosphere, and that is what's causing the warming. So those plants are, on one level, doing us a favor
Right.
uh, by absorbing some of that CO2. The ocean is as well. And one of the big questions is, well, how long can those systems sort of keep compensating?
So, you talked about, I guess the key issue is the balance, right? To maintain a planet that sustains life. So, we'll talk about, the disaster dynamics of this, but in terms of the general proposition and effect of on the Earth, how are these effects playing out as it affects our terrain and weather systems, sort of thing, and the atmosphere?
Sure. Well, we can already see quite a few different effects on the planet, both on land and in the ocean. Certainly, we see the rising temperatures, and that is more pronounced on land than in the ocean. Even though the ocean, the surface ocean, about the top few hundred to 1,000 meters of ocean, have already absorbed about 90% of that excess energy that I talked about.
Right.
That energy imbalance that's created by the added greenhouse gases has already been absorbed by the ocean. And 30 to 40% of the extra carbon dioxide has already been absorbed by the ocean. And those have effects on the ocean itself. So one of the effects is sea level rise. We can see that happening. That happens for two reasons. One, the ocean is warming, and as it does, it actually expands a little bit.
Okay.
Okay, so a warmer ocean takes up a little more volume because it expands like most materials do. We call that thermospheric expansion. Um, and also, one of the other effects is we've driven through the warming. We're driving the melting of especially so far montane glaciers,
Right.
um, and some of the polar ice sheets as well, especially Greenland and West Antarctica, are now in a state of sort of net melting. And that's driving another large fraction of the sea level rise. So we can see that sea level rising. We can see higher temperatures, especially we can see actually sort of it's in the statistics of heat waves, those sort of extreme temperatures in sort of extreme ends of the statistical distributions. You see those growing, and those are those very hot extremes that form the the hottest part of heat waves. And it's not only on land, we can see it in the ocean as well. They're actually marine heat waves. And those have their own ecological effects on systems like coral reefs and the Great Barrier Reef. So we see that. We also see a redistribution of rainfall. And so even in Australia, we can see that it's not so much that we're getting a lot more or a lot less rainfall. In fact, when you look at the stats, the statistics for our nation as a whole, you don't see a big trend. But what you do see is the southern parts of Australia, southwest WA, and the southern states, South Australia, parts of Victoria, New South Wales, getting drier, whereas actually things are getting a little bit wetter in the top end. And that's exactly what we would expect.
Right.
That's exactly what the physics of the climate system lead us to expect. So the rainfall patterns are shifting. We can even see it in the ocean,
Right.
in the ocean's saltiness and the distribution of saltiness.
So,
So
so it's not something that's going to be a universal desertification, for example. In Australia, that necessarily you might see the continent dry up even more. It will be a question of these rain patterns.
that's right. And one of the things that makes, I think one of the things that makes climate change and its effects so challenging in terms of how we respond to it is how variable in time and space the effects are likely to be. So it's not simply a question of every place is getting drier or every place is getting wetter or every place is getting hotter at the same rate.
Right.
It's really very heterogeneous, and that makes it challenging. It's also challenging for the models that we develop to try to understand and predict those changes or project those changes under different warming scenarios, because our models have gotten way better since I started working on things. Um, but they're still challenged to represent some of the variability on the space scales that people really live in and experience. So that's an area that was a lot of excellent research being done, and in by my colleagues in the Bureau of Meteorology and CSIRO and university groups and even state government agencies are really doing some excellent work on trying to understand what climate change means at that regional level. What does it
Right.
mean for you as a farmer in the Beaver Valley?
Yeah.
Are you as a state emergency service worker in
Yeah.
the Atherton Tablelands, so that's an area where and we're starting to understand that better and better all the time. But
So just on that one example of the southeast of New South Wales, and we have the Snowy Mountains and Snowy Hydro Scheme, and having a lot to do with those guys in that operation. What they tell me was, we haven't actually seen any change in precipitation here. It's just that it's not falling as snow as much. So that affects the skiing industry, for example. But then we had the millennial drought, that really played havoc with our farmers, including in places like the Beaver Valley. Was the millennial drought a factor of climate change, or was it just a really bad drought?
that question actually is a very challenging question, and a lot of people in my field, in the field of climate science, are working on just that. So it's not always straightforward because droughts are so episodic and so heterogeneous in time and space. It's not always straightforward to come up with a very clear 100% answer like this was caused by climate change. But climate change does have influences on the effects of drought. So one of the most important effects of drought is that it's not just a factor of a lack of rainfall. It's also a factor of how much rain is absorbed by the soil versus how much evaporates back into the atmosphere. One thing that warming can do is exacerbate that evaporation. So it can exacerbate what we call agricultural or ecological drought, which is the dryness of the soil, and that's extremely important for farmers. So there are a number of ways in which climate change can interact. So the driving forces that say cause a drought aren't at the moment that straightforward to always predict, but we do know that climate change certainly has the risk of altering some of the effects of droughts when they do occur.
Right.
And it's the same with floods.
So there can be contributing factors here, such as I know, like in our region, European farming methods and modern farming methods of how fertilization was conducted and laying on lots and lots of phosphate, etc., for example. And there were aspects of that which helped denude the landscape of carbon in the soil. And so and also you had these erosion factors and the rest, which I guess you could say, and you can concur or not on this, I'd like to have your view on it, is whether that contributes then to the effects of drought, and that has to be added to the equation.
It can, and certainly in the Climate Change Authority, we carried out some work on analyzing different options for carbon sequestration. How could you remove carbon? Something that we could get to maybe a little later in the discussion.
We'll finish up with
One of the options is to enrich the soil to a greater extent with organic carbon. And that can have, well, the effect, obviously, of storing carbon in the soil that would otherwise have been in the atmosphere, but also can modify some of the other soil characteristics so as to make it a little more resilient to the effects of drought. So it have some important co-benefits. Certainly, some of the people we talked to who are doing research on this were very much of the view that some of these methods to enhance soil carbon could also have other ecological and agricultural benefits.
right, make them a bit more resilient. And there was those theories too. You'll probably know about these, the natural sequence farming and whatnot, with how you slow water down in the landscape and aid retention of water as well. Has that been kind of factored in as well in terms of the mitigating some of the effects of climate change? Or
It's certainly being looked at. That's one of the things that people who are researching this are certainly looking at that, and again, trying to find where we can find sort of what you might say win-win situations, interventions that are good in terms of mitigating climate change, but also making these systems a bit more resilient to some of the impacts of climate change or other effects like drought.
right. And just in terms of, I guess, the chemical aspect, we mentioned earlier about the ozone dynamic being something that was kind of able to be addressed in a fairly short time and it recovered. But in terms of like these three main components of methane, nitrous oxide, and carbon dioxide, they have different, I guess, lingering effects and presence in the atmosphere, don't they? And so what's the difference amongst the three of those?
They do, and I'll start with carbon dioxide. And indeed, again, in my earlier research life, a lot of what I was looking at was the ocean's role in that long-term carbon dioxide cycle, and how it's responding to the human influence on the carbon cycle. So because carbon dioxide is mediated by these oceanic processes, which include the ocean acting as a buffer system. The ocean is a slightly alkaline solution. it absorbs carbon dioxide, and slowly over time, because the carbon dioxide has to dissolve in the water, make its way into the ocean, and then also interact not only with the seawater itself, but with sediments on the bottom of the ocean, which are effectively like a loose kind of limestone sediment. So it's acting like a buffer, like, you might take an antacid of some sort when you when you feel acid indigestion, people will, and that will be a similar kind of a buffering mechanism in the ocean. It takes a lot longer. So the long tail of this carbon dioxide is on the scale of thousands of years, in some cases, tens of thousands of years. And the long term, ultimate buffering of the system really is a geological process of the balance between carbon dioxide outgassing through volcanoes and then being absorbed through weathering processes on land. And so, again, that carbon dioxide that we've now relocated from geological reservoirs into the atmosphere will take some time to work its way through the system, certainly on a scale of probably centuries to millennia. So we have to sort of live with some of that for a while. Methane has a shorter cycle because of the chemical reactions that remove it in the atmosphere, has a mean lifetime, what we call a residence time in the atmosphere, of something like 11 to 12 years.
Right.
So it lends itself a bit more readily to some abatement, which potentially has a quicker effect. And there are quite a few opportunities to abate methane. Um, and nitrous oxide arises mostly from the application of nitrogen fertilizer and the way it's applied. And there are some agricultural methods that are now available or being developed that uh, result in less nitrous oxide coming out of agricultural systems. But nitrous oxide, similarly, is a very potent greenhouse gas and does last quite some time in the atmosphere. And so all these different greenhouse gases have warming effects that are different. So methane is a much more potent gas in terms of absorbing that outgoing infrared radiation, much more so than carbon dioxide, depending on the time scale you look at. It's anywhere from 25 to 80 times more potent, depending on what time scale you choose. And so because they arise from different processes, they lend themselves to different abatement approaches. So methane, a lot of it arises from agricultural practices. Not only we think of it in Australia, of course, because we have a very active cattle industry. Cattle and sheep, of course, are a source of methane, but also rice production and a number of other agricultural processes do produce methane. And so there's a lot of research being done on how to make those less emissions intensive.
Right. So in the rankings of villainhood, we got methane creates the nastiest effect, but is shorter lasting and can be remedial probably more easily in some ways. Carbon dioxide is going to be there for a hell of a long time, and then nitrous oxide somewhere in the middle of those two in the villain scale.
I would say carbon dioxide is so for methane. There are some really like readily available opportunities, especially where methane. One of the big sources is methane leaking from oil and gas production, what's known as fugitive emissions or fugitive methane, and that's a huge opportunity, or you might say low hanging fruit, where if you can detect those leaks, they could be remediated with, again, just better engineering practices. And certainly the industry, there's a long way to go, but I'd say that industry, is moving in the direction of doing a better job, partly because it's in their economic interest, of course, and partly because governments are, enacting policies that up that push industries in the direction of greater abatement.
Right, and we might come back more on that discussion in the second
Sure.
part. But to finish off this session, just in terms of using the ocean as the big carbon sink and soaking this stuff up, that has to have some kind of finite uh, outcome there in terms of what has been the effect on marine life, for example, having to absorb all this extra carbon.
I did some work on this in my other career, um, and we can see some effects. So all the organisms like corals that are reef building organisms, and quite a few planktonic organisms. They're just little small one-celled organisms that are floating around in the ocean, but are extremely important to the ocean's carbon cycle. Um, Many of those organisms, we can already see some effects on their sort of shell making or calcification processes. So we can see some effects already occurring. It's not clear what that does to those ecosystems, but we can already see some of these effects occurring. Some of my work a few years ago did document some of this in Southern Ocean.
Right.
That is one of the first pieces of work to show that this effect was already starting to happen. So again, the ocean, on one hand, is performing a service for us and taking up quite a bit of the carbon dioxide, but that also has effects on it, on some of its ecosystems. And again, there's still a lot of work to be done to understand how some of those ecological effects play out over time.
Right.
But we know it has effects.
Right. So we can't expect the oceans to continue to do the heavy lifting for us as the scale of this absorption increases. So we'll have to talk a bit about who else can start picking up the heavy
Right.
lifting load here in the next session.
Sure,
It's,
sure, sure. And look, it's a huge challenge. It's a global challenge and a long-term one, but there are a lot of opportunities to to solve it. So
it'll be good to
I'm actually
summarize
I'm
some of
actually
those.
optimistic
Yeah,
that we
that's
will
cool.
over time uh,
Yeah, no, we'll
solve the
be good to
problem.
unpack that. But look, thanks very much for that background. We'll really appreciate it. And so we'll finish the episode this week, having completed that kind of tour d'horizon of the whole issue, to coin a phrase. But thanks very much, Will, for that. I appreciate it. And look, thank you, everyone, for being with us for this session. I hope you found it interesting. It's very important that we understand actually what is behind the debates and the arguments over this and actually get to the scientific facts of it all. I know some people like to discredit science these days when it's not comfortable or it doesn't fit their worldview, but it is a good start point for us to be making decisions. So look, we'll see you again next time. We'll start talking about these issues about how it creates disaster effects for Australia in particular and what we might be able to forecast in the future of the impacts and also, as we flagged, what we might do about it all. So we'll see you again next time. Cheers.